Here we will show the model we offer to tackle the problem that SIMIO presents in the pulp and paper business logistic project statement. Next, we will see how the complex system proposed by SIMIO has been simulated through the following points. Brief review of the problem. Basic model with assumptions, animation, results, and validation. Improved model with initial ideas for improvement, measures implemented, and results. We will end with conclusions drawn from the developed process. Brief problem overview. The system consists of three main elements: loggers that produce wood, trucks that take it to the mills, and mills that demand a certain amount of wood daily. In this system, costs are generated associated with transport, acquisition of wood, and inventory. Our objective is to see with which operating policy we can minimize them. Base model assumptions, general considerations. In the system model, there are two aspects of great importance. The first relates to loggers, specifically their criterion of location in the area of study, and also their criterion of allocation to the mills. The second deals with the policy followed by each mill to request the quantity of wood needed, taking into consideration that it has no control over the logger, but in turn needs to meet their demand daily, avoiding penalties and stoppages due to lack of material. In the case of the base model, with respect to the first point, that loggers are distributed randomly in space and are also randomly assigned to mills. Regarding the second point, it is considered that each mill once a day requests an amount of total wood equal to its daily consumption. This daily amount must be contributed by the sum of the supplies of all the loggers that each mill has assigned. Base model assumptions, objects, features. Previously called elements such as logger, scale house, crawlers, and mills, these have been modeled by SIMIO Intelligent Object. The logger consists of a source and a server. The source is conditioned to generate entities based on orders arriving from the mill and available capacity according to the month of the year. Scale house. Each mill will have two servers that simulates the scale house of entry and exit with different processing times. Crawlers. Once the truck passes the scale house, a decision point is included, allowing for guidance of the truck to the operative crawler with less wait time. The mills have a sink where the entities are destroyed and also a parallel system of source and sink that is used to take control of the inventory. The mills must take stock of what they're asking for, what comes to them, and what they need to avoid penalties and stockouts. Base model assumptions, processes. The software allows for the creation of new processes that can better fit the situation we want to model. In this case, we've created processes associated with objects already defined, associated with time, or associated with specific events. For example, regarding objects, we have created a process to quantify the amount of wood produced by each logger or other for updating transport costs and inventory levels. On the other hand, there are processes which start at the beginning of the simulation, for example, to update the initial inventory, and others which are executed once a day, for example, the processes that assign the daily consumption or the total cost. Lastly, to simulate the penalties that are applied in case the inventory level drops below 20,000 tons, we have created one process associated with the monitor element of the software. The monitor element controls the inventory level in case the boundary is reached, the processes of penalty is executed. Base model, animation. How does it work? Here we can see how the system looks in the model. You can see the trucks going from the loggers to the mills and also the different colors assigned. Results. Simulating the operation of the base model for 2 years, the following results are obtained. Validation, transport costs. In order to validate the model, we will compare the results calculated based on an initial estimation of the results obtained by the model. We will do this with 3 concepts: transportation costs, wood purchase cost, and maximum production per logger. Here we observe the first case relative to the cost of transport, where in an initial estimation it was considered that a third of the loggers were close to the mills, another third were at medium distance, and the remaining third were far from the mills. We assumed an average of trucks per logger and an estimation of trips and turns of the trucks according to the month. The following result was obtained, which can be considered of the same order as the one obtained in the model. Validation wood acquisition. Regarding the cost of acquiring timber, an estimate was made based on the average daily requirement of each mill and the most restrictive production conditions of the loggers in the months of April and May. The following quantity of wood was obtained to be bought during the 2 years of simulation. This value magnitude is similar with the value obtained in the model. Validation logger production. Lastly, following the project statement, we calculated the maximum amount of wood that must be cut in order to maintain the growth-drain ratio. Through our investigation, we used data associated with oak that has 25 years of cut life cycle, and the amount of wood obtained is larger than the maximum amount of wood produced by the loggers in the model. In the case we use the 40-year period to regrow, given by the project statement, the result would be 70,000 tons, which is also higher than the amount of wood production obtained from the model. To get our improved model, we tried different logic and ideas where we can highlight. Organizing the loggers closer to their mill destination, allowing for an equal loggers distribution to each mill, allowing for a loggers amount distribution in function of the maximum inventory level, allowing for the wood request in function of an optimal and critical level, allowing for the wood request in function of each mill wood consumption. With this iteration, we saw different forms of optimization of our processes and reduction of costs in transportation, penalty numbers, and wood acquisition. Then we saw the model's behavior, and we concluded that if all wood orders are emitted at 8 a.m., the system is not efficient due to the high number of entities waiting to pass across the scale house of each mill. Therefore, we decided to try a new condition where wood orders are divided into 3 per day at 8 a.m., 12 p.m., and 4 p.m. It worked well, releasing trucks quickly. With all the ideas, we made an algorithm to reduce our experimental space following these steps. The logger was placed closer to the mill. The number of loggers for each mill was given according to the maximum inventory level of each. The wood request was divided into 3 times a day. Then we tried different scenarios for the logistics cost, where the demand in each case was the mill estimated consumption multiplied by a coefficient Fi. This was done for 3 mills. With all the different simulations, we saw that the comparison of scenarios should not be so direct, because if we bought less wood, we would pay less for it, less for its transportation, the inventories will be lower, therefore the logistic costs would be lower, but the stockouts numbers would increase. So we defined 3 indices for comparison, where the first one was to try to reduce logistic costs and stock out at the same time, the second to measure the effectiveness of the wood consumption, and the last one to analyze which is the real cost of the wood included in the average logistic cost. Finally, we decided to make 2 improved models, the first one just to compare the logistic cost, and the second one as a function of the real cost of the wood, which includes the wood price and the logistics extra cost per ton, where the difference is the daily consumption mill factor. Here we can see how the number of stockouts and logistic cost changes respective to the base case. Here we can see how the 3 indices change respective to the base case. Now we can see a comparison between the base case and the improved models, where we got a lower logistic costs for the improved model 1 with similar wood average production, and higher logistic costs for improved model 2, but with a high inventory average level. At the same time, our improved models reduce the number of stockouts, the amount of penalties, and the costs they imply. Finally, we get the 3 indices, and we can see that the improved model 2 is a better answer to the problem. In our opinion, improved model 2 should be chosen because it is synonymous with an efficient system both for mills and loggers. Thank you.